In this video, I'm going to be trying to demonstrate what standard deviation is and how to calculate it, as well as z-scores. So essentially, here's the issue. So I'm just going to create a new thing here for a second. So imagine I've got a number line, and I've got a bunch of values, and I find out, that my average value is 10, and I've got a whole pile of values that are close to 10. Maybe I have some the same. They're all sort of in the same area here, okay? So my mean equals 10. That number 10 does not tell me how spread out my numbers are. I could have the same exact type of graph. Maybe my mean is 10, but this time I got values way over here, like this, right? And I've still got a mean of 10. They're still sort of in the middle, right? But these numbers here are clearly more spread out than these ones are. Okay, we can calculate a number to figure out how spread out they are, and that will tell us that's called the standard deviation. Okay, so again, the mean doesn't really tell you how closely clustered the dots are around the mean. It just tells you what the mean is, and that sometimes is not all that useful. So standard deviation, basically what it is, it's going to give you a value that indicates how closely a set of data clusters around the center, which is the mean. So it tells you basically how spread out the data is, so how spread out the data points are. So it starts off with just deviation. And deviation, basically what it is how far away a particular point is from the mean, a single point. So the larger the size of the deviation, the greater the spread of the data. So there's a formula we're going to use. So for population, it's going to be your data point x. You basically just subtract the mean. So this is the symbol for mean on a population. So as a quick example, if x was 12 and my mean was 10, then that means that the deviation on this point is 2. It's 2 away from the mean. Okay, so that's your equation right here. That's for the single deviation of a single point. In a sample, it's the same exact equation, except they tend to use lowercase x, and for mean, they use x bar. Same exact thing. Take your data point, and you just subtract your mean, and that's how you get your individual deviation. Now this right here, this is actually not very useful. Like an individual point, knowing how far away it is, might be useful for that point, but generally in statistics, we worry about averages and stuff like that, right? So, oops. So the more useful version is called the standard deviation. And essentially what this gives you, I know this is going to be a sort of a dumbed down explanation of it, but basically what it is. It's sort of like the average distance, the average distance of the values from the mean. That's basically what standard deviation is. It gives you the average distance of each value from the mean. So there's two formulas we need. One's for population, one's for sample. Okay. The population, the equation looks like this. So it looks kind of like an O, but it's got like a little, kind of like a little hooky thing right here. This symbol is pronounced sigma. It's a Greek letter. They use this symbol to represent standard deviation. Now the equation for standard deviation looks like this. So it's a big square root. It's a great big square root. Inside the square root, we're going to have a fraction. On the top of the fraction will be the sum of all of the x's minus their mean squared, all divided by n, which is the number of items in the list, or the population size. This entire thing is square rooted. So this fraction, the entire thing is inside the square root. So where people make mistakes sometimes is they square root just the top, and that's not the case. You have to square root the entire thing, including the bottom. Now, for a sample, it's basically the same formula, except they typically use an S. It's a big square root again, same exact thing. It will be the sum of all of the x's minus the x bars squared, so that's the mean. And this time it's divided by n minus 1. Now here's the question. Why do I subtract 1 in a sample? This is kind of complicated. It's kind of hard to understand. Okay, I want you to imagine I was measuring the heights of students at a school. And imagine I've got, 1,000 students. If I measured every single student and I figured out the standard deviation, this is definitely going to be an accurate number. I can calculate this number, it will be accurate. But say, for example, I only grab 20 students out of 1,000, okay? There's a very good chance that I'm missing some of my outliers. I'm probably missing some of the people that are like maybe really tall or really short, or it's just plain inaccurate, right? Because the fact is it's a sample. I have not got everybody. So inherently there is going to be some variance or some kind of mistake inside of here, right? Because I don't have everybody. So what mathematicians have done is they want to artificially make the standard deviation a little bit bigger, because in reality it's probably spread out a little bit more because there's people we haven't accounted for in my example. So how do you artificially make this larger? Basically, you take that fraction and you subtract 1 from the base of it here. So instead of dividing by 12, you divide by 11, for example. And what that does is it makes the overall value of this larger, so when you square root it, you will get a bigger number. Okay, so because inevitably the sample or the standard deviation is probably larger than what you figure it is. So that's why they put this on here. This just artificially makes the standard deviation a little bit larger for samples. Now, the next number we can figure out, so these are just values. We can figure these out. The next value we can figure out actually is called the variance. And the variance basically is the square of the standard deviation. So for population, it's just going to be sigma squared. That's what variance is. And essentially what it is if you take this formula, if you square this, what happens if you square a square root, then the square root basically disappears. So the formula for variance essentially is going to be the sum of all of the x's minus the mean squared, all divided by n. For the sample, it's s squared. It's going to equal the sum of all of the x's minus x bars squared divided by n minus 1. Now, I would never ever calculate variance in this manner. What I would actually do is figure out standard deviation. I would get this number first and get the actual number, whatever it might be, and then literally put it to exponent 2, whatever that final number is, and that is your variance. So I wouldn't reuse the equation. I would literally just square the number, because that's what you have to do to get your variance. So don't get too hung up on this equation. It's the previous equation that you want to use more often, I believe. Okay, another equation you might need is the equation for a z-score. A z-score basically is the number of standard deviations that a datum, which is a data point, is from the mean. So the formula for z-score, if it's a population, would be this. Z equals x minus my mean, all divided by the standard deviation. So you have to have standard deviation first. That is not a 6. This is standard deviation. For a sample, the formula is basically the same. Sorry, sometimes I put little lines through my z so it doesn't look like a 2. So this is a z. Z is going to be x minus x bar. That's my mean, all divided by s, which is my standard deviation. Okay, so we've got the formulas we need. Let's try out an example here. So in this example, I've got a sequence of numbers here. So it's 5, 9, 9, all the way up to 16. We're going to do a couple things. First thing we need is a mean. And the mean is part of our equation. So the mean right here is part of both of these. So I need the sample mean or the population mean, depending what I'm working with here. So this one is a sample. So the nice thing about the question is it told us exactly what it is. So we're going to get the mean first. Mean is going to be x bar. Equation will be 5 plus 9 plus ... all the way up to 16. Add those all up and divide it by, if you count how many there are 12 numbers in this list. Divide that by 12. Okay, I'll let you use your calculator and punch it in, but I ended up with getting 11.58. That's my mean. Now, what I could do for my standard deviation if I go back and take a look at it, what I'm doing here at the top of the fraction is I'm literally, this is the sum of, so I'm adding up all of the x's minus the means squared. What I could do here is I could basically start doing this. I could go 5 minus 11.58 squared. There's the first one. Plus, because sum means to add, right? The next one, which is 9 minus 11.58 squared, dot, dot, dot. Okay? That's basically what you have to do for standard deviation. You got to figure that part of it out, okay? Now that can get kind of long, especially with 12 numbers. If I had like 4 or 5 numbers, I probably would just do this and work out the number. But because this is longer, I'm going to show you how to do it with a table instead. So this is a table that I've designed. I've got all of my data points listed. They're the exact same numbers here. What I'm going to do is I'm going to make a column here beside it, and I'm going to write x minus x bar. Excuse me. So what I'm going to do is my first value, I'll just write it up here what I'm going to calculate. I'm going to go 5 minus 11 point, what was my average? 58. So you work that out, you're going to get negative 6.58. That's the first number right here. So it's negative 6.58. I just wrote that there to show you how I worked it out. Okay. The next one you would work out is you would go 9 minus 11.58. The number you get here is negative 2.58. The next one would be the same thing. Then we keep going. 10 minus 11.58 is negative 1.58. And you just keep going. So I'll write in the answers. And you could work this out on your own. Excuse me. Okay, these ones will be 0.42 to become positive over here. 0.42. The 14s are 2.42. So I gotta move this down more. 2.42. Then we get 3.42 and then 4.42. Okay. So what I've done is I've basically subtracted each data point from the mean. So what I'm doing is I'm essentially trying to calculate, I'm on this one, trying to calculate this piece by piece. So if you think about bed mass, I've done the inside of the bracket now. I've worked that out. The next step is I got to square everything. So let's go back to our table here. The next step is to take all of the x's minus the x bars and square those. I'm going to take this column and square it. So essentially the first one, what I'm doing is I'm going negative 6.58 to the exponent 2. Work that out. You're going to get 43.34. Okay, there's my first value. 0.34. Okay. Do the same process in all of them. Take this negative 2.58 and put it to the exponent 2. You will get 6.67. Be very careful punching this in your computer. You might need to use brackets. This has to be a positive number. A negative times a negative must give me a positive because it's squared. A lot of people, what they'll do is they'll make mistakes, and essentially what it'll do is it'll square the number, but it'll leave it as a negative because what they've done is basically this. And when your calculator works it out, sometimes it'll do that. And you end up with a negative number. Be careful. These must all be positives here, no matter what. Okay, so I'll fill in the rest. Basically, I just squared up everything in this column and wrote the answer over here. Next one's 2.51, 0.34, and it's 0.17. See if I can scroll it all the way to the bottom here this time. It's going really slow. Okay, 0.17, 0.17, 2.42 squared, that's 5.84, 5.84, 11.67, and then 19.51. Okay, so there's all my values. Let's go back to the formula again here. So what I've done now is I've subtracted everything from the mean, or I've subtracted the mean away from each point, I should say, and then I squared it. The next thing I got to do is I need to sum them up. That's what this symbol in the front here means. It means to add those all up. So let's go back. That would be the next step in the process. So I'm going to add those up. So what I want now is the sum of all of the x's minus the x bars squared. So I'm going to add up this entire column. Go ahead and add them all up. You should get 102.92. So that's part of my equation now that's solved already. So I'm going to rewrite the equation here. S equals the square root of the sum of all of the x's minus the x bars squared over n minus 1. So if you look, I actually figured out the top part of the fraction already here. So I can write it in. So it's the square root of 102.92. That's the top piece of the fraction. All divided by 12 minus 1. Now you could go ahead and punch this in. Okay, so but make sure you go 102.92, divide it by 11, hit equals first, then square root it. The square root has to be the last operation. The answer you get is 3.06. Okay? So what does this mean? Basically what this value means is that the majority of the values or of the numbers is between, or they lie between 11.58, that's my mean, plus or minus 3.06. So this gives me a range. So you could figure out the low end and the high end. If you go 11.58 minus 3.06, the lowest value is 8.52. And the highest value is, when you add those, 14.64. So that's basically what this number tells me, is that the majority of my numbers fall between 8.52 and 14.64. Now, some of them are not in this category. Obviously, things like data point 5 is less than it, right? But the majority fit inside this range. That's what standard deviation tells me. Okay, so the last thing I'm going to do is the variance. That was what one of the other questions was. So variance, super simple. If we know the standard deviation already, all you literally have to do is square it. So in this case, it's going to be 3.06 squared, which equals 9.36. Now, variance is just another metric or another measurement for how spread out some numbers are. Bigger the number, the bigger the spread out, right? So it's super easy. That's why I said don't worry about the formula very much for variance, because if you got the standard deviation already, you can get this one really, really simply. Now, let's talk about another example, okay? So this is another example of standard deviation and how you interpret it. So in this example, I've got the heights of all the basketball players on 2 basketball teams. And for the Saints, their mean is 177, and the Falcons, the mean is 177 as well. The difference, though, is that the Saints have a standard deviation of 2.1, and the Falcons have a standard deviation of 14.7. So that's the only difference between the two. So what does it actually mean? So it means that the players on the Saints, they all have heights that are really close to 177. Basically, if you add and subtract this number, their range is probably around 175 to about 179. Okay, so add and subtract 2.1. So that's basically their range, 175 to 179. That's a pretty narrow group, so they're all around the same height. The Falcons, though, they have a lot greater spread. Their standard deviation is 14.7, which means you definitely have some taller people on the team, but you also probably have some shorter people on the team as well. So their range, you basically add and subtract this number from the 177, they're spread out a lot more. So that's what this number tells me. Okay, last question we're going to work out here. This is a Z-score question. So it says Tom receives a mark of 82% in Mrs. Trigg's class, while Tina receives a mark of 85 in Mr. Connick's class. If the mean in Mrs. Trigg's class is a 68 with a standard deviation of 8.6, and the mean in Mr. Connick's is 66% with a standard deviation of 10.4, which student had a better mark relative to their class? So to solve this, we're going to calculate Z-scores. Okay, calculate Z-scores. So let's do Tom first. Tom's Z-score would be Z equals, his mark is 82%. The mean of his class is 68, because he's in Mrs. Trigg's class. So it's a 68. We're going to divide it by the standard deviation in the class, which is 8.6. Do this calculation, you get 1.63. Okay, so therefore, Tom, right now, his mark is 1.63 standard deviations away from his average, or from the mean. Tina, her Z-score is going to be, she got 85. The average in her class is a 66. And the standard deviation is 10.4. When you work this one out, she gets 1.83. So she is 1.83 standard deviations away from her mean. So using the standard deviation, she's actually further away from the mean than Tom is. So therefore, Tina did better. So she has a better mark relative to her class than Tom does. So Tina did better. So again, this little example is just a little demonstration of how you figure out what a Z-score is. Pretty simple, actually. You just take the data point minus the mean, divide it by the standard deviation. Pretty simple. All right, so I did my best to try and explain what standard deviation is and how to calculate it, and variance as well. It's not really that difficult to do. It's just a lot of calculated work, and it's easy to make mistakes anywhere along the line. Okay, here's the homework for today from the book, and if you have questions about it, just let me know.